Finally, we have an outside factor here that will come into play. Instead of adding things on the outside or on the inside, we're instead going to multiply the function before I do anything to it. In this case, this a that is being multiplied on the outside can be any real number, but never 0. There's a reason why it can't be 0, and I'll let you think about that. Hint, would anything be possible if it were 0? This a gives us two pieces of information. One of them involves whether or not we're going to flip, and one of them involves whether or not we'll stretch or squish. Let's start with flipping. That's the relatively easy one to do. If a is negative, so if there's a minus sign outside of the main function for any reason whatsoever, the graph will flip upside down. That was Dotson being flipped over to look something more like this. However, if it's positive, nothing will happen. And we might get situations like that. A lot of the ones we saw before were actually those situations where no flip would occur. However, going into stretching and squishing, it gets a little bit trickier. It may not have been clearly seen in the GeoGebra adventure, but follow along. If a is bigger than 1 or less than -1, so for example, 2 would apply here, -5 would apply here, -100 would apply here, or 52 would apply here. This is a case where the graph stretches, or it actually holds up the boulder. However, if we have a situation where a is between -1 and 1, so something like 0.5, -1/3, 0.000001, all of those would work. In that case, the graph squishes. And that's the case where it gets crushed by the boulder. However, if a is exactly equal to 1 or to -1, we'll have no stretch or squish. Once again, kind of like flipping, we can have a situation where no stretch or squish happens. A reminder that stretch is where Dotson got a lot taller, and squish is where he becomes a pancake. Let's look at a couple of examples right here. If f of x equals 4x squared, note that this a right here equals 4. It is a positive number, so we have no flip. But how about a stretch and a squish? Well, let's look at the rules. A is 4, so it's a situation where we're bigger than 1. So when we have a bigger than 1, we know that it stretches. So we have no flip, and it stretches. Meanwhile, over here, for f of x equals -x cubed, this time, the a on the outside here, since there's no coefficient, we assume it to be 1, but there is a negative, so a is going to be -1. Since it's negative, we do have a flip. Now, with a being -1, which of these three rules is applied to? Whether a is bigger than 1 or less than -1? Is it the case where a is between -1 and 1? Or is it where a equals 1 or -1? You guessed it, it's when a is 1 or -1. So here, there's no stretch or squish. Dotson is just normal. He just got flipped flat on his face. Next up, f of x is 1/5 sine of x. Here, the a is on the outside of the sine function. So here a is 1/5. It is a positive number, so there's no flip. This time, between the three rules that we have, a is between -1 and 1. It doesn't reach 1 or -1. It's just sitting there in the middle. So when that happens, we have a squish. And it's a pancake now. Finally, f of x equals -10 times the square root of x. I haven't been stating it, but each time it is a multiplication. And that's what's important for it. -10 is being multiplied here. And that's our a. Since it's negative, we do have a flip. And this time, we're looking at these conditions. It's not between -1 and 1, and it's not 1 or -1 itself. It's sitting on the outs. So here, that means we have a stretch. I've seen students create a sort of number line before, with -1 and 1, to help indicate where we have stretches and squishes. Anything outside of this little range is the stretch zone. Anything inside the range is oftentimes called the squish zone. And anything that sits exactly on -1 or exactly on 1 indicates none. This graphic over here might be good. I'd go so as far as to draw an algebra fairy next to it, because I think it's pretty awesome.